Okay, hi, my name is Mojarradi. I am from Jet Propulsion Laboratory, and I'm going to talk about a subject that is of interest to all of you, I believe. It's a subject of about making the next generation mobility platforms for applications like Moon and Mars a lot more efficient, and I call it called Rover. So, a little bit of a background. If you look at the environment of Moon and Mars, they are they fit the classical definition of extreme environment. For Mars, the temperature changes from minus 125 degrees C to 20 degrees C. For Moon, the temperature changes from minus 185 degrees C during the lunar night to plus 20 degrees C. And so traditionally, how do we deal about in making mobility platforms that you see in these pictures, like the Mars Science Laboratory or Mars Exploration Rovers? How do we deal about putting mobility platforms on the surface of Moon and Mars? If you look at the state of practice, what you see is that traditionally we've put everything into what's called a central electronic box that is force-kept at Earth-like environment. This picture that you see over here is the warm electronic box that is part of the Mars Science Laboratory. The next picture is the Mars Exploration Rover and the warm electronic box that is over here. You see the wheels of the rover, and then this is the warm electronic box. The problem with that is that, number one, warm electronic boxes have to be force kept warm, and that takes a lot of energy. And then the central electronics have to be connected to the loads and sensors, actuators that are at the extremity of the spacecraft. So there is a jungle of wires that you can see over here, where one of my colleagues is testing them, that also are shown in here as the cables that does this connectivity. When you see over here in the Mars Science Laboratory, these are the wires that physically come out of the rover and go to the wheels. And those those wires physically are difficult to manage, especially when we go to assembly, test and launch phase, where any of these wires, if it's broken, you have to go and deal with tracing it back and so on. The other thing is that these large wires are very cause a fair amount of noise in the system and a major headache. Also, there is a mass associated with these wires, so and there's a heat loss associated with these wires, and so on. So, what is the concept of a cold rover? Cold rover, first of all, talks about the technology that would eliminate the need for warm electronic boxes. Once you don't need to have warm electronic boxes and electronics can survive operating at the temperatures of the NASA missions, then you can actually move these electronics through the loads and at the extremity of the spacecraft and save yourself also that wiring that you want. So a cold rover uses low temperature central processing unit, uses the low temperature data storage, uses low temperature capable digital interface. Then it has this, what I call a distributed architecture, where just all the loads and electronics are co-located with the loads at the extremity of the spacecraft, in particular distributed motor control, unified avionic bus, and point-of-load DC-DC converters that feed the power to these electronics. In terms of instruments that are in the payload, you can have low temperature capable instruments and sensors, and then low temperature capable actuators, low temperature radio, low temperature energy storage, and eventually you will have what's called a cold rover. If we can achieve that, we can realize about a 4x reduction in the total power that a rover has, and a 3x reduction in the overall mass of the rover. This is just initial estimates of what type of savings we could have with a cold rover. So the question is, how far is the technology in producing a cold rover? And we are not that far from doing something like that. So that picture translates into a list of physical modules that you can have, from cold avionic module, cold radio, and let me talk a little bit about each one of these. So cold avionics is one of the important parts of any spacecraft or any mobility platform. And at the heart of avionics is an avionic computer. Avionic computers are usually made with what we call a field programmable gate array that holds the computational code and executes that like a computer. So these gate arrays, there's a large number of them that are available from, and many vendors that make them. Actel, Xilinx are the two key vendors that quite often are credited with having a large gate array suitable for holding the source code and the design files, the designs that go into an avionic computer. So over here is looking at the question of whether we can run these gate arrays cold, and while the manufacturers do not recommend that, there is physical evidence that says that these components, these programmable gate arrays, are capable of operating at very low temperatures. Here are some of the data that JPL has taken on Actel and Xilinx. So the red is for Xilinx, Xilinx FPGAs operating all the way to minus 150 degrees C, and the blue line is for Actel FPGAs operating down to this lower temperature. And the news is really promising and exciting. So good news is that all FPGAs tested work to minus 125 degrees C, which is a Martian temperature, and they did work below that temperature, and some of them all the way to minus 180 degrees C, which is the lunar night temperature. So the next thing to look at as part of the modules that I suggested constitutes a mobility platform is communication and radio. So cold-capable radios. Question, can we make them or not? So here is the radio that was designed to operate the Mars Exploration Rover. It's a CTT-55 radio, and this is performance that you see here. It's only capable of operating to temperatures as low as minus 30 degrees C. It has 2 kilograms of mass and about 2,000 cubic centimeters of volume, and a power that is about 10 watts, and efficiency that for transmit and return that is 5 watts. I'm sorry, not efficiency. The power for transmit and power for return are 5 watts and 45 watts. In contrast, we designed a UHF cold-capable radio that is capable of running to minus 100 degrees C. It has a mass of 10 grams. It has a volume of 10 centimeters square. Its power efficiencies are shown here. It's not as high a power, but it does prove that we can look at physically developing a cold-capable radio that could receive commands and transmit signals for a mobile platform. So a mobile platform typically has motors and actuators that are driving the wheels of the motor. These are controlled by electronics we call motor control electronics, and this is the number of actuators that are in an MSL. So this picture over here shows the actuators that are amongst Mars Science Laboratory. And in MSL, you have a central motor controller that is connected to these actuators. Instead of that, we could use localized motor controllers on each wheel, and these are some of the trades that we have done that shows significant mass savings for that, and we have the technology to do motor controller and that would drive this in here. And the benefits are shown in blue over here, which in particular simplifies the assembly, test, and launch operation. So here is the technology that we have for building a code-capable motor controller. It's based on a NASA funded work that was done by a consortium of universities, JPL, Boeing Corporation, and BAE Systems. So it in its original original shape, it was a cube. It was a cube that had about 1,400 components and was weighing about 1 kilogram. And through silicon germanium CMOS ASIC integration, we have reduced it, or we showed that it could be reduced to the size of a credit card that is very small and could be sitting on every wheel of the rover. And we did actual thermal testing, and we proved that these ASICs are very capable of operating at low temperatures as low as minus 180 degrees C, suitable for operation of operation of the rover on the lunar night. Other silicon germanium capable ASICs that we have worked on are enabling the use of integrating instruments with the rover. This particular case is the exercise that we did with BAE System to look at the health monitoring of the X-33 spacecraft. This was the original box that was supporting the electronics that were used to look at the health monitoring sensors that were distributed on the X-33 spacecraft. This whole thing is getting reduced to a chipset that is like this, and the mass of 11 kilograms is getting reduced to about 100 grams, and through the use of code-capable silicon germanium CMOS ASIC technology. When you look at code-capable systems, the electronics are consisting of two parts. One is the physical transistors that are integrated into a chipset, and then there's electronics packaging. In other words, how do you put these chips next to each other on a package that is also capable for surviving the low temperature operation? So in there's two factors that are important. One is the choice of technology, and then the thermal stress that is associated with going through a temperature variation of from minus, say, 180 degrees C in lunar night all the way to 120 degrees C in the lunar days. That large delta goes beyond the glass transition temperatures of many of the material combinations that are being used for electronic packaging. And we have to come up with new material combinations that would do that, that would do the packaging and would survive the thermal shock that we see. At JPL, we have had what's called the thermocycle resistant electronics. We did that for Mars applications, which the temperature shock is less severe. It goes from 20 degrees to minus 125 degrees C. And we have shown that these recipes are capable of withstanding 2,000 cycles. In other words, that's about 3 years of Martian three Martian years plus margin. The same technology could be also applied to lunar applications. It needs a little bit of a refinement and optimization, and you can get there. Low temperature mechanisms is another system that is needed for doing low temperature operation at Moon for Moon and Mars. This is the mechanism that is being used for Mars Science laboratories. We have an equivalent set of mechanisms that are developed. This one uses liquid lubricant, and in here we use solid lubricants, and we can extend the actuation temperature down to minus 180 degrees C. And this is the cycles that we have run, over 100 million cycles on these type of actuators. And then low temperature energy storage is another way where when we have to operate at higher temperatures, when you have to operate at lower temperatures, then you have to deal with batteries that freeze out, and then capacitors that have their own problems. So this is a challenge, and in here, we don't have a battery technology that is capable of operating at lunar or Martian temperatures. In here, we still have to use force heating of the battery at lunar nights or at Martian nights. So the conclusion, let's look at the conclusion. Is cold rover feasible? I think these exhibits that I've shown to you suggest that it is, and we have hardware to show it to you. There is ways to go and to get them optimized for especially Mars. Get them optimized for especially Moon, but we are very close. And I think that we are in the brink of a change in the paradigm that will enable us to put in very efficient rover systems, mobility platforms on Moon using this type of technology. If we look at that, what are the benefits? We get 4 times reduction in power and mass and volume. We can have multiple rovers out of the same launch vehicle, more science instruments, new mission concepts for fast roving, opportunistic science, and enhanced autonomy. And also, we can enhance the robustness of for increased life. So these are the advantages that we have for next generation rovers if we use cold cathode technology. And with that, I'm closing my talk and I'm opening the floor for any questions that we can ask.